So do you remember this? In the bistable mode, just like I showed you at the beginning, here the output of the 555 IC is in the high state. Look, the output of the 555 IC is in the high state. When I say the output of the 555, this is exactly what I mean. So here, it goes into the high state, gets set, and you can see the path. Then, automatically, after a predetermined amount of time, it goes back down and gets reset. Moving forward to the next part, for the monostable mode, we can set up the configuration for pin number 2 in a very similar fashion to how we previously handled it back in the earlier bistable operation mode. Look, what we're seeing here is related to that initial bistable mode. Now, in this diagram where I want to talk about the monostable mode, we can use the same circuit that we had for pin 2 in the bistable mode and configure it the same way for pin 2 in the monostable mode as well. Now, in this part as well, if I press that button, the output goes into the high state. Now, to reset or reconfigure it, we need to look at how the discharge pin, which is pin number 7, works. Now, if you look at this diagram, the transistor's pin here is connected to the output of the flip-flop. Why do we say the transistor's pin? We mean the base pin of the transistor, because we have a collector, an emitter, and a base. Here, the transistor we see is connected to pin 7, and the base pin of this transistor is connected to the output of the flip-flop. Look, this is the output of the flip-flop. This base pin here is connected to the output of the flip-flop. When the output of the 555, and by the output of the 555, I mean pin 3, is active. When the output of the 555 on the other side of the inverter, this is the inverter, when it's low on the other side of the inverter, obviously the output of the flip-flop is high, which causes the transistor to be, so to speak, open, so that anything connected to the discharge pin gets connected to ground. You can see here that the ground, which is the same as the reference point, comes and connects it. So what happens is, when the output of the 555 is in the low state, the output of the flip-flop is in the high state, and it turns this transistor on so that anything connected to the discharge pin, which is pin number 7, gets connected to ground. So here, when we say the transistor is turned on, we mean the transistor is in the on state, which is also shown here as being in the on state. Now, in this diagram, whenever I draw something, make sure to follow those orange lines, because in these situations, those parts of the IC are active. Now, in this state, you can see that the output of the 555 is in the high state. The output of the flip-flop, or the not Q, is in the low state, and the transistor here is off, or in other words, it's in the off state. So what we do is connect the discharge pin, which is pin number 7, to the threshold pin, or pin number 6. If you look here, you can see that I've connected it to pin 6 using this wire. After connecting pins 6 and 7 here, I connected them to VCC through a resistor and then used this capacitor to connect it to ground. So pins 6 and 7 are connected to VCC and ground in this way. Now, what does this do here? Before I go to the previous slide, take a look at these orange lines. We said that in the monostable mode, we use exactly the same circuit for pin number 2 as we did for the bistable mode. When the switch is down here, it gives us the same path and we have a high output. Now, we said that in this setup, where I connected pin 7 to pin 6 and then connected it to ground and VCC through a resistor and capacitor, what does this do for us? When you look at it like this here, when the output of the 555 is in the low state, you can see, just like in the previous 2 diagrams, well, obviously, my flip-flop's not Q is in the high state, and this causes the transistor to turn on. When this transistor turns on, since it's also connected to pin 7, well, that's what happens. And we said that pin 7 here is connected to our pin 6, and in this way, we can use the transistor to connect pin 6 and the capacitor to ground. So in this state, my transistor is on, meaning it's active, and when I connect pin 7 to pin 6 through this capacitor, I can also connect pin 6 to ground. Now, when I come to this diagram, look, I want to switch this diagram. When we look at this diagram, pay attention to pin 2. Here, when I activate the button, that is, when I press the button connected to pin 2, just like we said before, my output goes high again, and this causes my transistor to turn off. Now, what happens when the transistor turns off? Let's go to the next diagram. Look at this part here. When the button is pressed down, it causes my output to go high, the transistor turns off, and here, when the transistor is off, no output from the transistor is sent to pin 7. In this state, pin 7 is connected to pin 6, and on the other side, pin 6 is connected to VCC through a resistor. Look at these pink circles here. This is the same current that causes the capacitor here to start charging from the VCC. See, it's like a circuit where the capacitor here is being charged by a power supply, and when my IC is in a state where pin 7, its transistor is off, it means there's no longer this connection here with the transistor. So, for example, pin 7 is not connected to ground anymore. Here, pin 7 is connected to pin 6, and the intersection of these connections is attached to the resistor and capacitor. At this point, when pin 7 is no longer connected to the transistor, that is, its transistor is off, it causes the capacitor in this section to draw energy from VCC, so to speak, and store it until, as you can see in this diagram, it reaches 2/3 of its value. And when it reaches above 2/3 of its value, which is for comparator 1, and gets charged, what happens then? Let's move on to the next diagram. Here, you can see that once pin 6 reaches 2/3 of the VCC value, it disconnects from the VCC and goes into a high state. The comparator also goes into a high state, connects to the reset pin, not Q goes high, and you can see that the output is shown as low for me, which means it's down, and this causes the transistor connected to pin 7 to turn on again. When it turns on, it allows the capacitor to discharge again, because when this transistor is on, it's connected to pin 7 and wants to draw energy, so it takes this energy from the capacitor since its connection to VCC is now cut off. In the diagram on the right, you can also see the capacitor section, where the capacitor is discharged in this way, and this process keeps repeating. Look, for example, right now, this lower part of the button is not in the connected state anymore. It's in the disconnected state, so that I can have this low output, which makes it use the capacitor, and the capacitor gets used up. Now you can see that the whole circuit returns again to this same place it started from. It goes back to where it was at the beginning, and it will remain in this stable state until it is restarted again. Now, we can control the capacitor charging time and the circuit's reset time by changing the values of the resistor and the capacitor. There is an equation for this, which is called the time calculation equation. As you can see here, the equation is like this: 1.1 multiplied by the value of the capacitor multiplied by the value of the resistor. Look at the diagram on the left. I have VCC, and I have the trigger input, meaning I have the input for pin 2, which you can see here is in the low state in this section and in the high state in this section. So in this part, it shows us a time interval for the capacitor to recharge again. That is, this interval that exists here, and is between the two dashed vertical lines, is what we want to determine. This is the interval that shows us when the capacitor is going to be charged. Now, when it reaches 2/3 of VCC, that is the voltage, at that point, our capacitor is fully charged. So at this point, our capacitor is charged up to 2/3 of VCC, and this causes our monostable output to be displayed like this. Now, if I have a capacitor here with a value of 1,000 microfarads and my resistor is 4.7 kiloohms, it will take 5.17 seconds for the capacitor to charge. Regarding unit conversion, let me say that here we have a capacitor and here we have a resistor. Obviously, their units are not the same, and there's no need for us to, for example, there's really nothing that requires us to convert farads to ohms. But the point is, we have microfarads and kiloohms. We know that micro means 10 to the power of -6, and what about kilo? Kilo is 10 to the power of 3, so we can apply these coefficients so that the units are in farads and ohms, which will give us the output in seconds. And when we multiply by 1 and 1, we get this value now. Now, for example, you might have a 100 microfarad capacitor and a 10 kiloohm resistor. So that's a 100 microfarad capacitor and a 10 kiloohm resistor. Do the calculation for this and see what the output will be. The output should be about 1 second for us. It should be around that. That means it takes about 1 second for a capacitor with 100 microfarads connected to a 10 kiloohm resistor to charge up. All right, the last scenario we're going to look at here, this has turned into quite a long marathon. I know, I hope you haven't gotten tired. I'm just saying, try to watch it as an engaging video, and if you have any questions, definitely ask. Because obviously, I'll try to explain everything that's here to you, but you might still have some questions, so go ahead and ask them. I'll answer these questions for you in separate videos. But again, I don't want you to get too caught up right now in wondering what happened with this or that. But just keep in mind how it works in the stable, monostable, and bistable modes. Basically, we categorize the operation of the 555 IC and circuits into these 3 modes. And then we add other components to the circuit we've defined here, and that's how we get the output. Now, as we mentioned, the last circuit, or the last mode we're going to talk about here, is known as the oscillator in the stable mode, and that's what it's called. Using this mode, meaning the stable mode, the 555 IC, as we said at the beginning of the session, doesn't need any input. But it automatically switches from the high state. Let's see how this works. Well, as we can see here, there's no button in this circuit because we don't need to apply any input to this part. I mentioned that in both the bistable and monostable modes, those buttons mean we're providing an input signal, but in the stable mode, we don't need to give any input. You saw its trigger in that first slide for the stable circuit. It was written as none, meaning we don't have a trigger or input signal. Here, just like you might remember, in the first circuit we built, pin 2 and pin 6 are connected together. While I'm explaining this diagram, take a quick look at the diagram on my right. That is, keep an eye on that capacitor as well. In this next diagram, pin 7, or the discharge pin, is connected to VCC through a resistor. Look, I actually forgot to show its connection here. Pin number 7 is connected to VCC, or pin number 8, through a resistor, and again through another resistor. Pin number 7 is connected to pins 2 and 6 via this resistor. So all 3 pins, 2, 6, and 7, are connected to ground through a capacitor that I placed here, which is also connected to pin 2. I don't know why I didn't connect these. It goes to ground, or in this case, my pin 1 is grounded or connected to the ground pin. Of course, it is very important to keep in mind that pin number 2 should be in a low state according to this specific diagram. Look, pin number 2 needs to be held in a low state so that the resulting output of our integrated circuit is maintained in a high state. Furthermore, the threshold, which is pin number 6 right here, should definitely be in a high state so that the output of the 555 timer goes low and gets reset properly. You want to ensure these voltage levels are precise to get the expected behavior from the circuit components shown in this layout. Double check your connections to make sure pin 2 and pin 6 are behaving exactly as we have described here for the reset sequence to function. Now, let's take a look at this diagram. When the circuit is connected to VCC, or in other words, to power, like I've connected it in this diagram, look, in this diagram, I've connected pin 7 to VCC like this. When the circuit is powered on and also connected to ground, here, you can see the ground is connected here, pins 2 and 6 prefer to follow a path that leads to lower resistance, meaning they end up at a point with less resistance. What does that mean? It means that if we follow this blue line, these blue circles here, if you pay attention, let's say, for example, there's a particle or that voltage coming from pin 6. It moves down this way and then over here, and eventually it connects to ground. So the resistance I mentioned here, where pin 7 is connected to pins 2 and 6 through this resistor, it won't take that path anymore because it's a longer route. You see, if it comes here, one path would be to go this way and for pin 6 to go through this resistor, but obviously it will choose the easier path to connect to ground. Consequently, looking at the circuit in this specific situation where it establishes a direct connection to the ground plane, the reset pin is held in the low logic state, and the set pin remains in the high logic state, for us within the specific configuration we are observing right now. So this specific flip-flop component, or the not Q output right here, is currently in the logic low voltage state, and the corresponding output signal right here is set to high for me. And what exactly does this demonstration show us about the circuit's behavior? As we mentioned in the monostable mode, when the not Q output, or the flip-flop output, or when my flip-flop output is in the low state, the transistor here is in the off state. That transistor connected to pin number 7 here is off, or in other words, pin number 7, which is the discharge pin, is in the off state here, meaning it's turned off. When the transistor is off, you can see this VCC here flows through. Now, that small voltage that exists causes, through the connection between pins 2 and 6, to come here and charge this capacitor. Look, we've written here that pin number 2 in terms of voltage and pin number 6 in terms of voltage are equal to the voltage across this capacitor C1. So the voltage source starts charging the capacitor. Through what path? Through these two resistors that are in its path. Why? Because in this case, its path is shorter compared to when it would be grounded. Therefore, as we said, pins 2 and 6 have a voltage equal to the voltage across the capacitor. Now, if you pay attention as we move to the right, the voltage across the capacitor is increasing. When the voltage of this capacitor exceeds 1/3 of the VCC voltage, it becomes charged. You might be wondering, well, at one point we said 2/3. Well, that capacitor was related to that part, to the time when it was connected to pin number 6. But here we have pin number 2, and with just 1/3 of the voltage, this capacitor gets charged for us. So in this case, when the capacitor reaches 1/3 of the voltage, comparator number 2 goes into the low state. The capacitor keeps charging until it reaches 2/3 of its voltage. When the capacitor goes above 2/3 of its voltage, reaching the VCC voltage, here comparative 1, which is connected to pin 6, remember we said pins 2 and 6 are connected? Pin number 2, through that VCC connection and the two external resistors, slowly begins the process of charging up capacitor C1. When it drops to 1/3, it goes into the low state, and when it increases again, since it's also connected to pin 6, when it reaches 2/3 of that value, comparator 1 goes into the high state. This causes, because it's connected to the reset button of the flip-flop, our flip-flop here to be reset, and the output of the 555 IC, or our output pin 3, goes into the low state. This causes the transistor connected to our pin 7, which is the discharge pin, to turn on, meaning it becomes active. When this happens, the resistor connected to this part is basically disconnected from the circuit, and from this point on, our circuit starts, causing the capacitor that was charged here to begin discharging. You see, at this point, the capacitor is decreasing in value and is discharging, and the voltage across the capacitor discharges down to 1/3 of the voltage corresponding to VCC. This allows the capacitor to discharge through that path, and the voltage across the capacitor drops to less than 1/3 of VCC. This causes comparator 2 to go into the high state and reset the flip-flop again. That is, since it's connected to the set button, it sets it, changes the output, and causes the output to go into the high state. When the output of the 555 is in the high state, that means not Q is in the low state, and this causes our transistor, the discharge transistor, to turn off. This, in turn, causes the capacitor, as shown here, to start charging again, and the capacitor continues to charge until it reaches 2/3 of VCC. This process keeps repeating over and over. The capacitor discharges down to 1/3 of its voltage, then charges back up, and so on. As a result, the output keeps toggling between high and low here. In other words, the output is either high or low, or, as we say, the flip-flop is in the high or low state. So in this way, we get this oscillating output, and this is how the unstable mode works. Now, if I want to briefly review these 3 modes so you can have a clearer understanding, I can put it this way. If you just keep these 3 points in mind, you've already taken a big step forward. If you want to see how it works again, you can rewatch the video from the beginning. A 555 IC in bistable mode can be selectively triggered so that our output is either high or low, meaning it can be in either the upper state or the lower state. The inputs can also be activated manually or digitally for us using a button. In monostable mode, which you can see its circuit here, a 555 IC can be triggered into the high state, and by combining a resistor and a capacitor, we can determine how long it takes for the circuit to automatically return to the low state. Regarding the astable circuit, we can say that a 555 IC in astable mode automatically switches between the high and low states, and again, this timing is controlled by an external resistor and an external capacitor. So keep these 3 points in mind to see how a monostable, bistable, and astable circuit work and what their outputs are like. Of course, if we want to understand these better, we need to actually build these circuits and observe their outputs in practice. In the upcoming sessions, God willing, we'll get into the practical side of things. We'll build the circuits we explained here and show you the outputs as well. Thank you for your patience and for sticking with me through this long session. The points that were mentioned needed to be said. I hope I was able to convey the material well. Otherwise, definitely ask your questions, because maybe during the lesson I forgot to mention something, and that could create confusion in your mind, like, why did this happen this way? But subconsciously, I might have thought, for example, that this is okay and that it's working this way, but for you, it might be a question. Be sure to ask your questions, because it helps your friends learn better, it helps you, and it also helps us provide much better lessons for you. Thank you for staying with me up to this point. I'd appreciate it if you like this video and share this channel with your friends. Thank you for your support. Until the next sessions, goodbye.